Hello, viewers. Today I want to talk about this paper called The Lottery Ticket Hypothesis. And it's a paper sort of in the realm of pruning, and we'll kind of go into that. But I'll go over the paper at like a high level first, and then I'll go over some like code that sort of like reproduces the paper in a smaller way. So let's get into it. So first, the main thing to start with is the idea of pruning is pretty central to the paper. So that's what we should start with. And pruning is just the idea of removing parameters and specifically removing parameters in a way where you keep the original performance or you don't really hurt performance. So let me give a visual example. Let's say we have a network like this fully connected. Let's say we find out which weights are unimportant and we prune those weights. We might have something like this. And it just leads to two things. It leads to a more efficient model because you have less parameters. So it'd be, theoretically less weights to store, less computations. And then that also leads to better generalization. So, there's this long-standing idea that the more parameters you have, the more complex it is, and more likely it is to overfit or not perform as well to data it wasn't trained on. And that's the main thing we want in machine learning. So that's the idea of pruning. With that, we'll move forward. So how pruning previously worked for this paper is that you would train a model completely. And with that trained model, you find out what parameters are sort of unimportant or which parameters you can remove. So you would have to do that training of the full model first before even pruning. So because of that, any sort of gains or improvement that we would see would be only during inference after training and not during training. There would be no sort of efficiency gains there because we trained the full model. Um, so that's sort of like the main problem this paper tries to address or at least help solve. And the idea or the question is, can we prune prior to having to go through that full training cost of training the full original network? Is there any hope that we can prune before that? So that's the gap. Is that let's say we train uh, the full original network, and let's say we prune some weights, and let's say we keep those weights as they were when we pruned it, and just do some fine tuning. So a few more iterations after pruning, train all the weights. Let's say we reach a performance A. If we were to take that prune network and sort of reinitialize it, train it from scratch, we wouldn't reach that performance A. So that doesn't offer any hope that we can sort of prune before training because uh, that's what we're doing and or at least simulating. And we don't reach that same performance as when we trained the original network, then did pruning. So that's the gap that this paper sort of addresses. And what they show though is that if you take that prune network after fully training the original network and you reinitialize it to the original initialization before training the full network, that can be trained from scratch and it matches the full, that performance A that we wanted. So that sort of offers, more hope that we can do pruning, you know, prior from having to go through that full training cost. Because let's say we find that network before doing the full training cost, like let's say there's some algorithms in the future that help you find those, uh, you know, prune networks before training. Then you can train it from scratch because that's what we simulated and show here. And yeah, that's the main improvement this paper offers. So the result is they show that this algorithm of, they give an algorithm which I'll talk about after this slide, but uh, the algorithm they use shows that you can sort of find a sub network, prune network from an original network that achieves comparable performance to that original network, despite pruning it aggressively down to like 10% or 20% of the original size, and then anything greater than that. So if you prune less than 80 to 90%, then sometimes it even pruning results in higher test accuracy, and that is just because of that sort of generalization factor that we talked about. So that's the result. And the approach, I think we talked about it a little bit, but you basically train a neural network from scratch. Then that's one and two. Then you prune some parameters and you create a mask M. That mask M is just zeros and ones. It's zeros for the weights that have been pruned and ones for the weights that haven't been pruned. So, if you're implementing this, you could just, there's this idea of magnitude pruning, and it's the idea of pruning weights that are the smallest. And that sort of works well enough. And so I think this is what the paper uses, and this is what I use in my implementation too. So we'll kind of go over that. But let's say we prune. Now we have a prune network. Now, if we reset the parameters to their original values, then you can sort of train this and it reaches good performance. But if you were to reset it to some random, initialization, it doesn't reach that same performance. So this will make more sense when we go over the code, but that's the main idea there. All right, so here's the code here. I'll just go over sort of at a high level. So here we're just loading the data, and we're going to be training a model on the CFAR10 task, where it's images, and you predict out of these 10 classes here, just like frog, horse, things like that. So that's the task, and we just load the data. We just show some images, show some labels here, and then this is the CFAR10 task and code. Some of it is from just like a general PyTorch tutorial. So actually a lot of it is. So, but yeah, let me continue. So going over the algorithm here, we start with one. We randomly initialize a neural network. So this is just done here, where this network is also from the tutorial, but what we do is we just randomly initialize it, and we save that initial state. So that initialization, which is here in the approach, it's theta 0. So it's the weights when you first initialize the model. We need to save that because here at 4, we're going to reset the parameters, that remain after pruning. We're going to reset that to that initial state. So that's why we save them there. So now we go over 2 is when we train the model. J iterations here is how they say. But yeah, I just trained for 12 epochs here, and show sort of the metrics here and the performance of the model. So we get about 61% accuracy, and F1 about 0.61. So that's the performance after training the full network for 12 epochs. So now we completed step 2 already. So already we completed 2 of the steps. Now we need to prune P% of the parameters in theta J, creating a mask M. So theta J is just the weights after training. And, we can prune however percent of the parameters we want. And we get a mask from that pruning. So after pruning, we figure out which weights are pruned. Those in the mask have a value of 0. And then the ones that remain have the value of 1. So we get that mask M from pruning. So now we do that over here, prune. And then again, it's just magnitude pruning. So the idea is that we prune weights that are the smallest. And uh, there's this sort of, you know, idea of iterative pruning where instead of just pruning once, you train the model fully, you prune a little bit, fine tune so that the remaining parameters adjust, prune again a little bit, and then you just repeat that instead of just doing one large pruning out at a time, at like one time. So that just sort of is a better approach usually. So here is just the pruning. I prune like 10% of the remaining weights each time. And you can see here the accuracy doesn't get worse. It actually improves each time. So that's sort of the idea that sort of aligns with the idea that as you move weights, the model becomes simpler and generalizes better. So that's after pruning. We have about 59% of the total parameters, initial parameters, and we achieve some accuracy like 64%. So this is just pruning so far. So now we have our mask M uh, from this, pruning step here. And our mask M has like 60% of ones than it originally have. So initially, all in the mask, it was all ones because we didn't prune yet. But then after pruning, we keep 60% of the original parameters. And so, 60% of mask M are ones because of that. So now we go over to step 4 here. And step 4 is the idea of resetting the remaining parameters to that initial state that we saved. And here they call it a winning ticket. And what a winning ticket is just a prune network compared to the original network where you can train it from scratch, train it from that initialization. And here, that math shows that. So theta 0 is the initialization. And this is an element-wise product. If you do that with M, then you just keep, it's going to be 0 wherever the weight, wherever you have weights that you pruned. So that's the winning ticket if you train that from scratch and keep those prune weights to 0 during training the whole time. Then you reach comparable performance to prior to pruning. So here, just to sort of recap, we trained the full network 12 epochs, and it achieved 61% accuracy, 0.61 overall F1. And then we pruned, so we found the prune network through pruning. Now let's try resetting the parameters. So first, I wanted to show that if you reinitialize like to something else, not to the initial parameters, it doesn't reach comparable performance. So here we just start from scratch, try to train that prune network from scratch to like random initialization. And as you see, we don't reach that 61% overall accuracy. So this is training 12 epochs from scratch. And then we also don't reach that 0.61 F1 score. So that's the gap that this paper sort of improves on. And now if we instead still training from scratch that prune network, we reinitialize it to the initial initialization. So prior to training anything, if we reinitialize it, and then we train at 12 epochs, this would be the winning ticket. So it's the neural net with the initialization, and then the mask saying which weights are pruned and which aren't. If we train at 12 epochs, now we reach way better accuracy. So this is even better than training the full network 12 epochs, which was 61% accurate. This one's 63% accurate and has a 0.63 F1 score. So that's what the paper showed as well. Like if you don't prune that aggressively, then sometimes it even has better performance than the original network. So that's what this shows, and that's sort of the code. So yeah, that's the code. It empirically aligns with what the paper states. Uh, I hope my explanation of the paper made sense. And thanks for listening.